All right, welcome back. So early on, I think it was the first video in this section, I talked about why you should know or care about binary heaps. Yeah, they come up in interviews. Yes, they're taught in pretty much every computer science course, but also they're used really commonly to implement something called a priority queue. And I gave like a 5-second rundown of what a priority queue is. And I said we'd come back to it later. We are now doing just that. We're coming back to it. We're going to explain in more detail what a priority queue is, give some use cases for it, but then also implement one using our binary heap code. So we won't have to write a ton of new code. It's really just modifying what we've already done or duplicating it and changing a few things. So that's what we're going to do here. But first, let's just understand what a priority queue is. So according to Wikipedia, it's just a data structure where each element has a priority associated with it. And elements with higher priorities are served before elements with lower priorities. So we have a collection of data, and each node, each element has a priority associated with it. And we want to basically be served, that's passive voice, I guess. We want to retrieve, we want to take one element at a time out of this list or this structure, whatever we're using to store it. We want one thing at a time that we're going to tackle next. Just like in an emergency room at a hospital, you have a bunch of people waiting. Everybody is assigned, internally at least, some sort of priority level. And then a nurse or a doctor comes out and retrieves one person at a time based off of that priority level. So, somebody who walks in with a gunshot wound is going to be seen before somebody with a scratchy throat, for example. So anytime you need to manage data or information of varying priority and have things, that you're inserting and they may not be the lowest priority. You're not inserting things in order. You might be adding something in. Like in the ER example, someone walks in with a gunshot wound. Well, there could be 100 people who were there first, but they all have the flu. The person with the gunshot wound is going to be seen first. So a priority queue should account for that. It always serves the highest priority element. Here's a more real-world example. On Unix machines, on every machine, there's a bunch of processes happening behind the scenes. Thousands of different things that are running behind all the magic of your computer. And you can view it, or view a lot of them at least, on a Unix machine by typing the ps command. And I've added in some additional options, but what it's showing me here is the process ID. And then here, it's technically not called priority, it's called nice, but it is a priority level. And you can see they're pretty much all the same, but then we have certain things that have a higher level or higher nice value, which actually means a lower priority, I'm pretty sure. So if 0, all of these are going to be basically served in the order that they are added in. But then occasionally there's something, let's see, is there anything else? Come on, there's got to be at least one. There we go. Here we go. This thing has a nice level of 10. It's just a priority, or same thing here. This is another thing for Adobe, apparently. So I am not the person to explain how this all works. I know very little about the underpinnings of your operating system and what's happening behind the scenes. I basically know how to find one of these and stop it if it's broken. And that's about it. But what I'm trying to illustrate is that there's a ton of things happening at any given point on your machine. But at the end of the day, there's an order. They're not just all going at the exact same time. Things are being served or being worked on in an order. And there's a priority that each element gets, which is used to determine that order. Another thing worth knowing is that priority queues are separate from heaps. They are just an abstract concept. You could implement a priority queue with an array or a list, which I'll show you in just a second. It's not a great version, it's slow, but it's possible. It's just like when we say list, the idea of a list. Well, you could have a list as a linked list. You could have a list implemented as an array. There are different ways of implementing them. It's just a generic sort of abstract concept, a priority queue. So you could go about it like this. You could use an array or a list and just store things as they come in. So something's inserted, you put it at the end or at the beginning. And then when you need to remove something, when it's time to serve the next item, you would just iterate over the entire thing and just check what's the highest priority. Keep a variable. We start, okay, priority 3, that's the highest. And then we hit 1. Also, it's worth noting, oftentimes a lower number actually denotes a higher priority. So in this case, if we're working for the lowest number, we would start here. Okay, the lowest number is 3. Then we get to 1. Okay, well that's lower. So this is our new element that we're going to serve, but let's keep going. Nope. This is still greater. This is greater. This is greater. Then we hit the very end and we realize, all right, this is the highest priority thing we're going to serve. The lowest number, the highest priority. So that's not a great approach because every single time we need to serve something new, we have to go all the way through and compare something to every single item, because it could be at the very last node, it could be at the very first item. It's not a nice way of doing it. It's simple, but it's naive. So, as you've already probably surmised, we're going to use a heap. So here's an example of how we could do it. This is using a hospital sort of metaphor, emergency room. People walk in and they have different injuries. So at first, our heap is empty. There's one person who walks in with a low fever. So they're going to be the next person to get help. We always remove from the top or from the root of our heap. Right now, there's only one element. It is the root. So they get help first. But let's say that before they get helped, someone else walks in. They have a concussion. That is a higher priority element or value, right? They need to be seen before someone with a low fever. A high fever, that's up for debate. A low fever, though, I think they can wait. Just take a little Tylenol or Motrin, whatever you take. So the person with a concussion are the next to get help now. They are the root. Someone else walks in and they have a lower priority. Well, we don't put them at the root. It's a heap. So this value is less than this priority. So they're going to be below it. It's a child of this parent. So we're still following the rules. Whether this is a min tree or a min heap or a max heap, it doesn't really matter as long as we're consistent. So what we end up with is the concussion is going to be served. They're the next person to get help. But then someone comes in off the street with an exploded head. It's not good. And they need help immediately. So when we insert something with a higher priority like this, it's going to, remember how this works, we add it to the end and then we bubble up in our heap. So if we added it here, we bubble it up to the top, we end up with exploded head with the red priority is the next thing to get help. Then concussion is its first child, then the drunk person, then the low fever. But really all that matters is what the next thing is. And then someone else comes in, they have the flu. Well, they're not as high a priority as an exploded head. So we're just going to put them here for now. So then let's say the exploded head person gets help. So what happens? Well, we remove this node from our heap. And remember what we do is we swap it with the last node and then we have it sync down to the correct spot. And this is what we end up with. So now our heap is serving somebody with the next highest priority, the person with a concussion. And if we were to remove this one again, we would end up with the new root as the flu. So everybody who has a yellow priority will be served before everyone with a green priority. Anyone with a red priority is served before everyone else. Anyway, it's kind of a convoluted explanation, but that's how a priority queue works when you use a heap. All that we care about is the top level element, the minimum or the maximum thing. And every time we add something in, that could potentially be updated. Every time we remove something, we always remove from the top. And so there's going to be a new element there that wasn't there before. So a heap works really well because insertion and removal they have a time complexity of log n compared to if we just did this naive version. If we had let's say 1,000 elements in here, every time we wanted to remove something, if there was no order to them, we were just comparing every single priority to find the lowest or the highest. We're working with O of n time complexity. So if there's 1,000 elements, we're talking about 1,000 comparisons roughly. So that's not good. That's not a good version. It would work, but if we use a heap, it's much faster. Okay, so that's an explanation into what a priority heap is, or priority queue is using a heap. But again, you can implement them in other ways, but a heap is a classic one. On Wikipedia, it goes as far as to say that many people confuse the two or conflate the ideas because a priority queue is so commonly done with a heap. But again, it is an abstract concept. You can implement it in many ways. All right, so next up, I'm going to give sort of my overview, the pseudocode for how we could implement our own. And then after that, I'll have a solution.